In the previous lecture we introduced momentum conservation, and in particular we started to think about a momentum budget for a control volume. And most of the time we spent our time thinking about momentum flowing in and flowing out of that control volume. And we also touched a little bit on surface forces on this particular control volume, because that's a force on the control volume and it's part of the momentum budget. So one of the reasons for introducing momentum conservation last week was to provide a context for introducing hydrostatics. So normally in fluid mechanics, statics is taught separately to momentum conservation, but in fact the best place to understand statics problems is to imagine you've got a momentum problem where there isn't any momentum, and you've still got to balance the forces on a particular volume of fluid because it's static, it's not moving, and there is always a force on the fluid because of its weight, so it has a mass and it's in a gravitational field. So we introduce hydrostatic forces through a special case of momentum conservation. Okay, so there are two aspects or two uses of looking at statics. One is to measure the pressure distribution in a fluid, and typically that's a column. And the other application is to measure force distributions on surfaces. So this might be required if you wanted to build a dam. And we're going to deal with that in the next lecture. So in this lecture, we're just going to look at the relationship between weight and the pressure caused by this weight. So the classic example is a manometer. So if you can imagine you have a tube of water and it's under the liquid and there isn't any air bubbles in it, and you carefully turn it upside down so the open surface of the tube is under the level of the fluid and the closed surface is above it. So there's no pressure in this region, so it's a vacuum in this gap here, and there's pressure in the rest of the atmosphere, and this weight of fluid corresponds to the pressure acting on this surface and pushing this fluid up this column, and there's no pressure here, so there's no force pushing down on this fluid. So this height of liquid corresponds to the atmospheric pressure, ambient pressure. And historically, people used mercury to work out atmospheric pressure. So you may have heard that atmospheric pressure is typically 760 millimeters of mercury. And they use mercury because atmospheric pressure for mercury is a typical scale that you can have in a laboratory. So a third of a meter kind of thing. Okay, so that's how a sort of a manometer works, or a single height manometer anyway. And so people can use this principle to work out pressure differences. So in this particular case, there's a pressure difference between vacuum, which has zero pressure, and atmospheric pressure. So that height corresponds to atmospheric pressure. And if you've got a chamber here that you want to measure the temperature, what you can do is you can measure the height difference between your pressure that you're trying to work out and atmospheric pressure, and this height here gives you the pressure difference between atmospheric pressure and that pressure in here, and this pressure difference is called a gauge pressure. Okay, if this pressure was atmospheric and this pressure was atmospheric, then this H would be 0. We can also use pressure differences to measure the velocity of fluids. And so this is called a pitot-static tube, and there are various configurations. And as we will discover early next term, the pressure in a moving fluid is different to the pressure due to a stationary fluid. So in these three examples we have three different types of manometer here. So in this particular case we've got, so this first U-tube manometer, we've got one leg of the manometer open to atmospheric pressure out here, and there's no fluid motion here. And this leg of the manometer is in a flow, and the flow's going past this gap here, and so the pressure at this point is different to the pressure on this point, and we measure this height. And if we do a few calculations that we'll come across next term, we can work out the fluid velocity based on this height difference. And another configuration is that we can put the tube in the middle of the flow, and at this particular point, right on the end of the flow here, the fluid comes to a stationary point, and this is called a stagnation pressure, and we'll come across this next term. And this stagnation pressure in a moving fluid is different to a stagnation pressure outside of the fluid, and this gives you another height difference, and you can measure the fluid in this way. And the standard way of having a pitot tube is you have both legs connected to the fluid, so you have the fluid stagnation pressure on this one, and you have another pressure here which is called the dynamic or the static pressure, and this also measures your fluid velocity. Okay, so we want to relate the pressure difference to the fluid properties in this particular lecture. Okay, so as I stated, this is going to be an application of the momentum equation where there is no momentum. So what we're going to do is we're going to take a control volume and we're going to assume it's static. So there's a force equilibrium, and these forces must balance. And the forces that we have are the weight of the fluid and the pressure distribution over this particular control volume. Okay, so this is our derivation. So what we're going to do is we're going to imagine we're under the surface of a fluid, and we're going to take a small element of fluid. So we're going to construct a small cylindrical control volume, and we're going to put it at some angle theta to z. So z is the vertical direction, and the acceleration and gravity is acting in this direction, but gravity is opposed to this z direction. And we've got a certain mass of fluid in our cylinder, mass m, and the force or the weight of this fluid element is mass times the gravitational acceleration, and this gravitational acceleration acts downwards in the opposite direction to z. And we also have a force distribution over the surface of this control volume due to the pressures acting on this surface. Okay, so we've got two coordinate directions here. We've got the z coordinate direction, and we've got the L direction, which is the coordinate direction along the axis of our cylinder. Okay, and we're going to make a balance between the two forces: the pressure force distribution on the control volume surface and the weight due to the volume of the fluid in this particular control volume. So let's deal with the weight. So if we wanted to work out the weight, we've got the mass and we've got the magnitude of the gravity vector, So the weight acting in the z direction is minus mg. Okay, because this is the z direction, so we're saying that this is the positive z direction, so the force is a negative force, and it's minus mg, so m's positive and g is positive. And we know that the mass is equal to the density times the volume of the cylinder, and we can work out the volume of the cylinder by saying, well, we know what the cross-sectional area is, we'll call that delta A, and it's dl long, so this dl gives us the volume. And we said we're going to resolve the forces in the L direction, so we need to resolve the force that we have acting in the Z direction in the L direction, and we use that by taking the component of the force, this mg force acting in this L direction. So we effectively take the cos theta part of this force. So this is the magnitude of the mg acting in the z direction, acting in the L direction. Okay, so this deals with the weight, and we now have that acting in the L direction, and then we do a force balance in the L direction for the forces due to the pressure. Okay, so we've got forces on the ends, and we've got forces on the curved cylindrical section, because a pressure will always act normal to this. A pressure force will always act normal to the surface, normal. And if we think about the cylindrical section, all of these forces are acting normally to the L direction. They're acting normally to the axis of the cylinder. So therefore, these the forces on the curved sections of the control volume don't contribute to this force balance that we're doing, and so therefore we need to take the force balance based on the ends. So we say we have a pressure at this particular location, and this pressure at this particular point is P, and there's a certain area, so there's a certain force, PdA, that's pushing in this direction, and we're saying we don't know what the pressure is up here, so we'll say that there's a small change in pressure between this level and this level dz, and we'll say that change is delta P. So we've got a slightly different force acting on this particular direction, and these two things are acting in opposite directions, so they will have different signs. Okay, so when we want to work out the net force due to the pressure, we've got P plus delta P, so we'll say that this is the positive force, so this means my L direction is from this point positive in this direction down to PdA, and we've got PdA here, and this is negative because this is opposing the direction, so the net pressure force is dPdA. Okay, so that's the net force that's the net pressure force on the surface of this control volume. So because it's a static problem, and this control volume is stationary, the forces must balance, so we can say that the pressure force must equal the weight of fluid acting, the force due to the weight of the fluid in the control volume, so these things must be equal. So then we can say that, well, we've got this relationship as long as the fluid is static, and then we can transform this a little bit. We want to get things in terms of dz, so we can say that dz is equal to dl cos theta, and we can put a dz in here, divide both sides by dz, and we end up with dp by dz is equal to rho g. Okay, so this is we started off with these small changes, and as we shrink our control volume down to 0, then we get to the differential form. So this is the gradient of pressure with z at a single point. Let's call it, it's a total derivative, and it's equal to minus rho g. Okay, and this is our master equation. So we're going to use this, and this is the thing that we use to work out pressure changes of height in different liquids. And we just have to be a little bit careful about our sign. So you have to choose the correct equation depending on where your coordinate system origin is, and in particular, does your coordinate system direction go with or against the acceleration due to gravity. So typically what we'll do in the atmosphere is we say that z equals 0 is ground level, and z increases as you go up into the atmosphere, and we know that gravity acts in the opposite direction. So in this case, pressure is going to decrease as you go up, and you need to think about the gradient. Is the pressure is dP by dz going to be positive or negative as we change z? So if pressure is going to go down as z is going to go up, then the gradient is going to be negative, and we should be using this one. On the other hand, if you want to do a calculation underwater, for instance, you will typically choose your z equals 0 position to be the surface of the water, and z's going to increase, and the pressure is going to increase because the gravity is acting in the same direction as z, and so therefore dP by dz would be positive, and we would be using this form of the equation. So when you're doing calculations and solving problems using statics, very important to draw a diagram first of all and decide where your origin is, which direction your coordinate is going in, and in which direction your gravity vector is acting, because otherwise you can get yourself in trouble. So what can we do with this equation? Well, typically we want to work out the pressure, and if we're going to work out the pressure, we need to integrate it. So your go-to integration of this equation up to here is we move the dz up to here, and then we can integrate the left and the right hand side. So if we integrate integral of dp, we end up with p, and then we end up with the integral of rho g dz. So once we've got to this integral of rho g dz, g we don't have to worry about because that's constant, doesn't depend on z, but we have to be a little bit careful about density. So if it's an incompressible fluid, we generally have no problems. We can take the rho g outside this integral, and then we've just got the integral of dz, which just gives us a z, and then we end up with an integration constant. And the integration constant is the pressure where z is equal to 0. So normally we would end up with an equation like this. So if we think back to our example that we had for atmospheric, working out the pressure change in the atmosphere, if you like, P of z, which is this thing here, so the pressure at some height z is going to be equal to atmospheric pressure. So this is the pressure at z equals 0 minus this pressure due to the height. So this pressure as a function of z is called the gauge pressure, and if it's incompressible, the liquid is incompressible, then or the fluid is incompressible, then it has a linear relationship of pressure with this height interval here. And because it's linear, this means that this rho gz is very easy to use as a pressure indicator or a pressure measurement method, because all you have to do is measure z, and then you've got the pressure change directly. You can also take this equation and divide both sides by rho g, and then you have an equation that has dimensions of length, and then you have P over rho G. So typically you have this P over rho G term has units of length, and normally it's called a head. So you might hear plumbers talking about what's the pressure in your house, and it might be that you've got 10 meters of head, and they would be talking about water, because that's the fluid that they're interested in. Okay. Can get a little bit more complicated if density varies. So this means we have to do something with rho. So that means we have to get rho in terms of some function of z, and then we can integrate this entire integral. So first example might happen if you've got a liquid that its density is a function of temperature. So you might have a reference density and then a corrector based on the local temperature, and this temperature might vary as the height. So this is a reference temperature, and this is how temperature varies with height. So this alpha and this beta would be constants that define these two things. So if you want to do this integral up here, you have to substitute those two things into this equation. So we've got rho minus alpha t, and we know that t is this thing here, so we can substitute that into here, and now we've got an equation where we've got some constants, and we've got something that's a function of z, so we can integrate that, and we end up with this equation here, and an integration constant c that we would have to get from the question, which would be a boundary condition. Another example is typically, or you can do equations looking at pressure change in the atmosphere, and in this case you would use the gas law. And so here we've got pressure and density and temperature that are all related. So let's assume, for instance, that RT is a constant, and so therefore we can have minus Rg, which is effectively Pg over Rt, and then we've got effectively this, and we can do the integral and work it out in this way. Okay, so these are the kind of things that we need to do with our dp by dz is equal to plus or minus rho g. Nice example of the kind of things that we would ask you to do is we have this geometry like this, and we want to know what the pressure is in our piece of equipment, and we want to work out this pressure using a manometer. And in effect what we have to do is we have to relate this height to this pressure, and the question is, well, how would I do it from first principles? And you would do it like this. So first of all, what we do is we take point number A and we say, well, what's the pressure at point number A? And it's equal to the pressure in my piece of equipment, so it's Pg, plus the pressure due to the weight of the fluid in this part of the manometer. So this is rho g, and Z1, an acceleration due to gravity. So this PA is equal to the pressure in my unit, so this is the thing I'm trying to work out, and the pressure in this leg of the manometer. And then I can do the same thing, and I can say, well, what's my pressure at point number B? So this is at the same height as point A, so it means that this pressure and this pressure are the same, and this pressure here is going to be equal to whatever the pressure, whatever is going on above this point. So that's this PA, which might well be atmospheric pressure, and the height of the fluid above point B, which is rho G, rho F G Z2. So that's what we've got here. And then we make our conceptual leap and say, well, these two pressures must be the same because they're at the same height. So then if we take one equation away from the other equation, we end up with this equation that says my gauge pressure, or if you like, the difference in pressure between the pressure in my equipment and ambient pressure up here is equal to this expression on the right hand side. Okay, so this is your kind of master equation for a manometer. And what people normally do is they use manometers to measure the pressures in gases, and they usually use liquids to measure the pressure in gases, and typically the density of a liquid is maybe 1,000 times the density of a gas, so you can normally do, without very much approximation, you can say that the gauge pressure, effectively the pressure in here, is just related to the height of this liquid. So this is your Z2. Okay, so that's typically how a pressure measurement would be done to work it out in a U-tube manometer. Okay, so what have we done? We've used momentum conservation without any momentum to do a force balance on an element of fluid, and that force balance made use of the weight of the liquid and the pressure distribution over the surface of the liquid, over the surface of the control volume, and we derived a differential form for that, and we made a quick note about the sign convention and gave an example of how to use this equation to work the pressure difference in a manometer. Okay, thank you very much.